You all were yesterday here, na? So ये सब enter वाली. So we talked about climate change, greenhouse gases, and all those things yesterday. Slightly touched upon hydrogen. And this morning we had a look on conventional hydrogen production process by steam methane reforming. But today we'll move from conventional method, which is very carbon intensive hydrogen production, to cleaner hydrogen production. So we'll look at the different colors of hydrogen. Probably you might have already heard about grey hydrogen, brown hydrogen, blue hydrogen, pink hydrogen. There are so many colors, so we'll talk about those things. We'll look at the economics, going from brown to green. So how the capex and opex change to go from brown to green. We talked about the energy transition yesterday, how the electricity production is moving from carbon intensive sources to renewable power, transportation. We also looked at some industrial applications, right? And we found that some of the industries are really hard to abate. We cannot replace the energy sources that we are using at the moment. So we'll look at the hydrogen, which is also a hard to abate industry, how we can use hydrogen there. We already saw yesterday there is a price gap between dirty and clean. How the government policies are on the hydrogen side, right? And then finally, energy carriers, which can carry this hydrogen from one location to other location. So to start with the different colors of hydrogen, so probably green, blue, and grey is more familiar, but they have even more colors here. So purple, pink, which is, let's say, electrolysis hydrogen production, but the energy supplied is via nuclear. So it's basically there are three: grey, conventional source, which is natural gas, and blue. Blue means you produce grey hydrogen, but then capture the carbon dioxide and sequester it somewhere or utilize it somewhere. That's blue. And green is absolutely using no fossil fuels, so purely based on electrolysis to use renewable power or green power to generate hydrogen. So that's basically here. And you could imagine greenhouse gases footprint, CO2 footprint for the green hydrogen will be almost zero. Also for the nuclear, really zero. We also have another color, yellow, which is something between green and blue, or maybe blue and grey. That means you are using hydrogen production via electrolysis, but the electricity you are using is not purely green electricity. So you are still emitting CO2 somewhere else. So the CO2 footprint theoretically for green hydrogen will be zero. For nuclear also theoretically is zero, because we are not using any carbon intensive fuel. For yellow it's a little bit more than zero. Talking about blue hydrogen, so whatever we'll see in coming slides, how much the CO2 footprint or how much CO2 we emit per ton of hydrogen production. And we said blue is the one where we capture all this carbon dioxide. But there is a limit, you cannot capture because of the equilibrium of every process. So economically, you can capture up to 90-95%. Nowadays even higher, but up to 95-96 is optimum. So you will still have some CO2 emissions, right? So a little bit higher for blue hydrogen than yellow. So that's the order of, let's say, increase of CO2 footprint. Then there was another one, Turkish hydrogen. I think we talked about, you know a little bit of this. So basically this is the pyrolysis method where you simply heat up the methane gas at very high temperature and crack your methane between carbon and hydrogen, elemental carbon and hydrogen gas. Somehow similar to grey hydrogen where you have natural gas and you kind of crack it between, but unfortunately it's cracked between CO2 and hydrogen. And in this case it's purely carbon. The advantage of pyrolysis is the energy requirement is much lower, because direct cracking of methane is not that endothermic. Although temperature requirement is high, but the reaction heat is much lower. So in a SMR process, we saw this morning, unfortunately some of you were not here, the hydrogen process, you have CO2 emission because you are burning natural gas as fuel, but we saw from the PSA process, the tail gas, carbon monoxide, CO2 and unreacted methane, that also goes to the fuel system. So out of every 10 kg of CO2 we release for the grey hydrogen, 3 or 4 kg comes from the fuel system. Right? And if you have a reaction process where your endothermic reaction heat is much lower and you need much lower fuel. So comparing grey hydrogen and turquoise hydrogen, in turquoise one you will have much lower, 20-30% lower CO2 emission. Now you can make the turquoise and blue mix together, or you have turquoise hydrogen and you either use this carbon, elemental carbon, finds its application, alumina industry where you have electrodes, some other application where you can use this graphite particles, right? But wherever you use it, finally it will end up as CO2. Because these graphites, after 10 years, 20 years of use, will be burned somewhere. So that's not the ultimate solution. So blue hydrogen you see as capture and sequester somewhere in geological formation for maybe thousands of years. That's considered a permanent sequestration or fix, but not related to this one. So grey we already talked about based on natural gas. We spent almost 1.5 hours this morning looking into details of the process. And brown and black is nothing but using coal, different kind of. So this morning, yes.
Production of hydrogen through biomass, biomass pyrolysis or gasification will be as turquoise.
I think biomass gasification without carbon capture would be somewhere similar to blue one. That means because we are releasing CO2, but CO2 is coming from biomass, and we consider that this biomass is generated from CO2 coming from the atmosphere. So CO2 footprint wise, if we have hydrogen production without carbon capture using biomass, it will be somewhere close to blue hydrogen. And if you have biomass as your feedstock and produce hydrogen gas via gasification or whatever, and capture the CO2 and sequester it somewhere, you will have negative emissions. So negative CO2 footprint.
Yeah.
So it will be even better than green hydrogen. That's what people are talking about, thinking about this.
Yeah.
Because biomass use, you consider it as CO2 coming from atmosphere. So like for natural gas, the CO2 you have to take into account. But when we do the CO2 footprint for the biomass gasification based hydrogen production, we take zero CO2 carbon coming in the system, because this is from the biomass, and biomass is nothing but atmospheric CO2. So this morning, as I said, we talked in detail about the conventional process using methane, and the green one, blue we already talked about. It's nothing but the conventional process with CO2 capture, and the most, let's say, on the other extreme is electrolysis based hydrogen production. Within electrolysis also there are, let's say, two major technologies available: alkaline electrolysis and PEM, electrolyte membrane. So this is an established technology. I think in the chloralkali industry they use it for many years, where hydrogen is a byproduct, chlorine industry. So they are making use of this technology now to go from chlorine production to hydrogen production. Very well established. There are a lot of licensors, suppliers provide this such electrolyzers. So since it's already for many years existing, scale is very high. That's why the cost is already down. So somewhere around 1,000 euro per kilowatt. The PEM is the new one, latest one. It's already industrialized. Many electrolyzer-based plants are coming up with this technology. Cost is a little bit high, still high because it's very new. Advantage-wise, between alkaline and PEM, you'll have relatively long startup times for this one. This can start very fast. Another comparison or disadvantage between these two is the efficiency of this one was slightly lower, somewhere around 65%. So when we say efficiency here, in terms of energy, whatever kilowatt hour we put in as electricity, only 65% will come out as hydrogen, as energy. So this one is somewhere around 65, 66. This is already touching 70%, so a little bit higher efficiency. There's another aspect between these two. So when we say efficiency is 65%, let's start, or let's say when your electrolyzer or cell is new. But with the time, your efficiency starts dropping. For example, in solar PVs also, they guarantee for 20 years, but a certain efficiency, that 90% efficiency is guaranteed for the next 20 years. So efficiency drop for alkaline is also high for the same period of time. So this one is really picking up fast, and future will be dominated by PEM. Then there is another one at somewhere between lab to industrial scale, which is a solid oxide electrolyzer. Efficiency is very high. Just to go to basics once again, between both of these technologies use pure water, or purified water, demineralized. And difference between these two and this one is, this one uses steam. So once again, the heat balance we talk about, we are supplying water, and then we are taking out hydrogen gas. Right? But if you can supply water as steam, you are already putting more energy inside the system. So efficiencies are as high as 80%. Right? So it's very efficient, but as I said, still somewhere between lab scale and industrial scale. So a little bit higher scale, people are already building up. Some are already operating demonstration scale plants. But if this one hits the market, and if we have higher efficiency, 80-85%, that will be very good, because you could see 20% rise from these two technologies to this one. But when we say we have to supply steam, that means we have to supply energy somewhere else to produce steam from water. Right? And good thing about this one is, this can be integrated with other industries. What we saw in the morning, that we have steam co-production, and nobody is there to give us value for this steam. We cannot sell this steam. Sometimes, in some cases, I've also seen even the steam is sent to the air cooler and just condensed and energy is lost. Right? So, from integration point of view, there's a lot of advantages. So you have high efficiency, and somewhere you get very cheap steam, which can be used to produce hydrogen at very high efficiencies. So as I said, currently still under development. Right? And since it's still under development, cost is pretty high. So once economy of scale comes in, you start producing a lot of electrolyzer stacks, and then the price will definitely come down. So CO2 footprint for hydrogen, I think we talked about this slightly last time. But we saw in the morning that for producing 1 kg of hydrogen, we need somewhere around 14 megajoule of energy. Right? And we also did the costing, it's somewhere around 1.5. We saw from one of the graph in the morning, we produced globally somewhere around 90-95 million ton of hydrogen globally. And 1 kg of hydrogen releases somewhere around 10 kg of CO2. If you do a simple calculation with the reactions we saw in the morning, CH4 plus twice H2O gives CO2 plus H2. You can already see you end up already somewhere around 5 or 6. And then as I said, 40%, 30% is coming from fuel burning. So if 1 kg of hydrogen releases somewhere around 10 kg of CO2. 95 times, you already see almost 1 billion tons of CO2 annually is only because of hydrogen production. And we saw yesterday the annual CO2 emission globally is somewhere around 30. So hydrogen industry is a major CO2 emitter, no? Almost 3%. So on the first slide we saw different colors of hydrogen, and as we said, the main colors are basically grey, blue and green. Anything else is somewhere in between. So here I am showing just a small comparison how the CO2 footprint and cost-wise they look or compare with each other. Right? So let's stay with first two first of all. So the grey, this number we saw in the morning already, 1.5 euros per kg of hydrogen. That's my production cost. CO2 footprint we saw somewhere around 10. And the blue one 2.5. And as you said, we can only capture 95%. For sake of simplicity, I assume now that I capture 90% of this CO2, then I am left with only 1. But actually, capturing will also cost some energy, right? And this will also release some CO2. So capturing 90% CO2, that means you avoided 85%. So that's the difference between capturing and avoiding. Right? Because when you capture 90%, you need some energy. For this energy, you're also releasing carbon dioxide. So effectively, we are avoiding only 85%. Capturing 90%, but avoiding 85%. Because for this energy, we are releasing CO2 somewhere else as well, right? So that's how this 10 became 1.5 for the blue, right? Now, yesterday we talked about this, why somebody will start capturing CO2 or why somebody will start producing blue hydrogen suddenly. So we talked about this carbon price, carbon taxes. So let's assume there is a carbon tax of certain euros per ton, right? But what it means, if you are emitting some CO2, for every ton of CO2 you have to pay, let's say 100, 120 euro, right? So I just try to calculate at what carbon tax people will start moving from grey to blue, and it's around 118 euros per ton. So 1.5, I simply do a mathematics here. So I try to do these two, match these two numbers by varying my carbon tax. So what it means that somewhere around carbon tax of 120, the blue hydrogen starts making sense. Carbon tax is not existing currently in many countries. Only few countries started with this carbon tax system. Netherlands is one, and they set 120. So in Netherlands, you can say based on these assumptions, blue hydrogen, everybody is moving from grey hydrogen to blue hydrogen because they can do 1.5. They can produce at 1.5, keep emitting 10 kg per ton, but then they have to pay 120 euro to government as tax, right? We saw yesterday electricity production from coal to renewable power, what's the cost difference, and this famous line, getting clean is expensive, right? This is what we see here as well, the hydrogen price of 1.5 from grey and 6.5 to green. So for electricity, the ratio was 2, but for hydrogen, the ratio is almost 5, right? So 1.5, almost 6.5 here. So why people will start using, producing is fine, but why somebody will start using green hydrogen and pay 5 times more price? So once again, the similar comparison or similar sensitivity. So if the CO2 tax become even higher, 505, then the price of grey hydrogen is matching with the green. So this kind of CO2 tax we need to really push people to start using green hydrogen instead of grey hydrogen, right? Just to extend it further, did the same calculation or same comparison between blue and green. So we started with green and blue, grey and blue, and the grey and green. And now you could see very high CO2 tax required to match blue with the green. Right? questions? You capture carbon dioxide, put it in your beverages, drink your cola, and CO2 is released. That's the pressure on the CCU route, right? Once again, to repeat, energy transition we talked yesterday for electricity, industrial heating. We saw this slide yesterday as well, the disparity between the locations. As we said, we are blessed, we are somewhere around here, 2,400 hours of good sunshine every year. Some countries like European and Russian, Northern Russian, they are not so blessed. Right? So CO2 footprint of grey hydrogen, you could see China suddenly sharp increase in the total mix, and that is in parallel to their growth story from 2000 to 2020. They started consuming a lot of hydrogen, and as we said in the morning, as in India, compared to in India where we have most of hydrogen production by natural gas, in China it's mostly by coal gasification, which is even more CO2 intensive. So we saw yesterday already for the electricity. Now we will see the same thing for hydrogen. Unfortunately, renewable potential at place where consumption is low. So you could see the northern African regions, Middle Eastern regions, they have very good solar radiation, solar potential. But if you look at the consumption, it's only this much, right? So what we can do, we produce at low cost places. You produce, let's say, hydrogen via electrolysis here and transfer it to the locations where it is required. So most consumers are in this region, Northern Europe and Northern America. Right? But we saw yesterday already talked about this transport of energy from one place to another place. We talked in terms of electricity. Losses somewhere around 8% for 1500 kilometer, transmission and distribution losses. If you can correlate with the high school electrical courses, power is voltage times current, right? And your losses are I times I square, current times resistance square. Right? And that's the reason why for the long transmission lines they always ramp up the voltage. Up to 140 kilovolt or even higher. While at home we use 220 volt. So if they start transmitting electricity at 220 volt, you will get hardly anything at home. Everything will be lost. So that's okay for short distances. We see 8% for 1500 kilometer. So within country like India, that's fine. India within countries, one country it's also acceptable. 1500, 2000, you already crossed 3-4 countries there. So there also it's fine. But if you are talking about intercontinental, because we want to produce here cheaply and transfer it there, which is something like 7,000, 8,000 kilometer. Similarly, 4,000, 5,000 kilometer here. That's not a good idea. Another issue is there's a big ocean here, and overhead transmission lines are relatively cheaper. You can do that, but subsea lines are very expensive. So first of all, if you are talking about 5,000 kilometer, you already have 30% losses. You have to invest huge amount of money. So the difference what we had in electricity, 174, 79, if you remember from yesterday, everything is lost. Right? What we can do, we can transfer this electrical energy into chemical energy somehow, right? And transfer this chemical energy stored in the compound and transfer this compound, right? So, what is the main requirement for this compound? It should have high energy density. So you're transferring 1 kg of compound or whatever material, it must have very high energy density, very high energy content. It should be ideally non-toxic, non-flammable, non-explosive. Right? Should be socially accepted. Yesterday somebody was making a comment, hydrogen for mobility, yes, but you also don't want to see hydrogen, people are scared, those kind of things also. Socially should be accepted for the society. Unfortunately, we do not have any such compound which fits all these requirements. That people accept it, and it's non-toxic, non-flammable, non-explosive. There is only one thing we talked this morning is steam, water, which can carry a lot of energy, but transferring steam from one place to another, you could imagine lot of heat losses, lot of condensation. So it's also not a good idea for kilometers and kilometers. For few hundred meters, that's fine within the plant, but not in. Yeah. So in next coming few slides, we'll see comparison between 4 methods. So what we can do, lot of electricity, solar electricity here, green electricity here. You produce hydrogen here. You can liquefy hydrogen here, and via tankers, ship tankers, you can transport it somewhere else. Right? That's one method. So that's the one. The first one is you don't change your component. You don't change your compound. But what else we can do? We convert this green hydrogen produced somewhere in Middle East or Northern Africa into synthetic natural gas from the renewable hydrogen, and transport this natural gas to somewhere else, convert it once again to hydrogen with the process, using the process what we saw in the morning, the steam methane reforming, and use hydrogen there. Or the synthetic natural gas can also be used directly. Right? We'll see in coming slides in detail about these processes. There are some other organic compounds. So this is like direct conversion, and this one is second one gives us opportunity to use the energy directly as natural gas at the location where it is required, or we use it, we convert it to hydrogen and then use it. Right? There is another way. There are some organic compounds which you can hydrogenate. So hydrogenation means addition of hydrogen at one location. You transport these compounds somewhere else and then dehydrogenate it and release hydrogen you can use further. Right? So that's another way. Another interesting compound is ammonia. Haber-Bosch we talked yesterday about. So you generate green hydrogen, convert it to ammonia, and transport ammonia, and then once again crack the ammonia between hydrogen and nitrogen. Nitrogen you release into atmosphere, hydrogen you use. So the first one, as we said, we simply generate in the Middle Eastern or Northern African regions where the renewable power price is low. If you remember from yesterday, 174.89 or 79, sorry. So you generate hydrogen via electrolysis where the price is somewhere around 80, right? You liquefy it, and via tankers you ship it to somewhere, you regasify it and go to the hydrogen network, right, to use. Now, problem with this method is electrolyzer efficiency is coming up, new methods coming up, we are reaching 80%, fine for this step. Problem is with this step. We saw in the morning the boiling point is very low for hydrogen, minus 252 degrees centigrade. That means a lot of energy is required to create this cold temperature. Right? And within this step, you lose almost 25% of your energy. So every step you need electrical power. So whatever hydrogen you put in, some electricity you have to put in. What comes out is only 70% of what you put in as hydrogen. So 30% already lost here. Now, hydrogen being lightest component, another problem. And when you transport these into the ship, it's liquefied at minus 252 degrees centigrade. It means it's very cold. And these voyages can take up to 3 days, 4 days. And you could imagine a lot of heat radiation into these tanks. Although they are well insulated, but still you have a lot of heat ingress. That means you will always have some gas, some liquid boiling. Right? That's actually called boil off during the journey from point A to point B. Sometimes this boil off gas is recovered because you have to supply electrical power. You can compress it back, so it's not lost. But sometimes electrical power on ship, you could imagine, very expensive. So sometimes this boil off gas is simply vented off. So because of its inherent characteristics, very low temperature, right, and very low molecular weight, there's a lot of boil off during the journey. Right? So that's also another disadvantage of this process. You regasify. Regasify means you reach at liquid condition and you simply boil it. Right? Since the temperature is minus 252, it's a very good thing. You could use this cold energy, refrigeration, some other process where you need really cold temperature. So you could do some integration here with some other industries where you need cold temperatures, but if it's not there, then regasification will also cost something. There's efficiency loss, another 2-3%. It's not much, but there's some efficiency loss here in this step as well. So altogether, it's not a very good idea. People are doing it because no other option is available at the moment. But the round trip efficiency going from this point to this point is somewhere around 50%. You lose already 70% here. That's a low number. So the next one, synthetic natural gas. You take CO2, generate renewable hydrogen and convert it to methane. Water is simply discarded. The advantage of this route is natural gas society is handling for last 100 years, a little bit less than 100 years, but it's a very established technology, very established supply chain. Right? And there are some hard to abate industries which we talked about yesterday. There we cannot replace natural gas, so we continue. So natural gas will be there in some of the applications, right? And if this natural gas is not the natural gas exploited from gas fields, it can be considered as clean. We'll come to this in a few minutes. But all in all, natural gas will be there to be used in hard to abate industry. So that's, and also it's an established one. Infrastructure is there, pipelines are there. So everything is there. It's just the method we could generate or produce natural gas is different, but that's a strong advantage of this route. The major disadvantage with this one is if you are using this natural gas somewhere else, CO2 is released, right? So solution for this is what you do, you generate, as we saw on the previous slide, you generate green hydrogen by electrolysis, right? You do methylation, that's this reaction, right? You combine CO2 where this CO2 is coming from. So generally you have this CO2 either by burning natural gas or something else, right? But in this case, we'll come to this later. So you generate natural gas and liquefy it, which is also very well established technology. LNG, probably everybody has heard about liquefied natural gas. You ship it. There are almost 700, 800 LNG ships operating every day. It's a very well established supply chain. Everybody is familiar with this. And you receive liquefied natural gas, gasify it, and produce hydrogen gas using process SMR process, which we saw in the morning in detail, right? So this is conventional, well established. This is well established. This is very well established. So that's a major advantage of this route. You are doing something new. This is also pretty much established, right? The only new thing you are doing here is you are capturing CO2 in this process, and the captured CO2 goes back. So what people are proposing is a ship will bring natural gas, right? It will unload all the liquefied natural gas to the plant, stay there, and this plant will produce CO2, and this CO2 will be put in the same ship. The same ship will be go, otherwise the ship will be going empty. Right? So you make use of the same ship, it goes to the other location, taking the CO2, giving this CO2 to this methylation process, and that's how CO2 is only traveling here to here. So there is no additional CO2 emission apart from some boil off. But boil off in CO2 transport is much lower because, does somebody know boiling point of CO2? Minus 57 compared to minus 252, it's much lower. So you have much lower heat ingress and much lower boil off. So that's basically, this showed some advantages, some disadvantages. It's very new. People have already started building plants and transporting CO2, but actually they are transporting on one side energy. So this is energy carriers, right? Energy transport, and other side you are just transporting this CO2 because this CO2 is mixed with your hydrogen and then it becomes a molecule which is carrying actually the energy. We'll see in coming slides there is another major disadvantage with this one, or maybe we can discuss already here. So hydrogen being the lightest gas, even after liquefying, the density is somewhere around 80 kg per meter cube. Right? Compare this with the water, it's 1000 kg per meter cube. So much lighter liquid. Even when we liquefy it is much lighter. So when we were transporting liquid hydrogen, we had pure hydrogen, lot of energy in 1 kg, right? But now you could see, if we compare hydrogen with natural gas, right? So if we have 1 kg of liquid hydrogen, we need how much? 16 by 4 kg of natural gas. Right? So actually, in the same ship, so the ship transport you could imagine is based on per kg. What do you have as a measure? It's the weight which is defining your fuel consumption for the ship transport, right? So when I'm transporting liquid hydrogen, for example, 1 kg, if I do it via methane, it's only 4 by 16, right? That means my transportation cost for this route will be much higher because I'm transporting much lower hydrogen compared to pure hydrogen. Right? Okay, the third one is ordering components. So toluene and methyl cyclohexane are some examples. So you do hydrogenation and dehydration, as I said. Advantage of this method is the operating conditions are mild, or let's say milder than others, so 20 bar to 20 degrees centigrade. And round trip efficiency is lower compared to H2 and SMG as carrier, right? But the disadvantage is you still have some hydrocarbons in your chain. And when we are talking about the zero carbon economy, there will be no crude oil, there will be no hydrocarbons, so there will be no toluene or methyl cyclohexanes coming out, right? So that's the major disadvantage people are talking about for this one. But as we said, you generate once again renewable hydrogen, you hydrogenate it, right? You transport it, you dehydrogenate and take the hydrogen to your network or to your use. You generate the same compound what you started here. In the same ship, you put the same compound, goes back, it's rotating like this. So that's another way of carrying the energy from one location to another location. And just to repeat once again, this energy, solar PV disparity radiation that brings this option, this idea to generate solar energy or hydrogen, green hydrogen in one location where the renewable power cost is low and transport it to the place where we need it. Then the last one is ammonia. So ammonia very well known, used in refrigeration and many other applications. Transporting ammonia is also very well established. Liquid ammonia density is somewhere around 760 kg per meter cube, not like very low like liquid hydrogen. So you could transport a lot of ammonia in your tankers, right? Yeah, I already said ammonia already 100-year-old technology similar to SMR what we discussed in detail this morning. The major advantage of this route is the round efficiency is much higher compared to others. It's almost 90%. What it means, if you go from here to here, you have only losses of 10%, 15%. Right? So that's a major advantage. One disadvantage is ammonia is highly toxic, not highly toxic but toxic, right? And handling needs a lot of additional safety infrastructure. Capex becomes high. So small ammonia use is fine, but if you have higher capacity and within your plant ammonia inventory is above certain limit, you need to install a lot of safety measures. It increases your capital costs. So you are ending up here with ammonia, and then you can crack this ammonia to get your hydrogen. The nitrogen is released. Good thing about this is you do not have any transport back, which this ship of course will go empty back, but will not use as much as fuel as something else. So at the end of the day, the overall cost is much lower for this route, right? You can also people are also starting to think about using ammonia directly, because this route will also have some efficiency loss. So what you can do, you can directly use your ammonia. Some gas turbines are already using ammonia with natural gas. So slowly they are increasing ammonia content in their fuel to generate power. But ammonia conversion is not easy. It's a very lazy combustion. The flame is not stable, so it's a lot of problems. Another major disadvantage using ammonia as direct fuel is, we talked about it yesterday, high NOx emissions, because you have ammonia and oxygen and at high flame temperature, so NOx concentration, NOx emissions are much higher. So you need more investment to clean your flue gas. So some qualitative comparison between these four methods. A lot of numbers here, but we'll spend 5-10 minutes on this slide. One way is, as I said yesterday, we saw the difference between the renewable power 174 and 84, right? And we are talking about, or we talked about in the last 15-20 minutes, that we can generate at low cost and transport it to somewhere else via 4 different methods, right? So the first column you see here is, let's say, at high cost center or cost place, you generate renewable power at a cost of almost 9 euro per kg of hydrogen. Then you don't have any shipping cost, you don't have any boil off. It's the same. So you are at the same location, so this price is similar. You will understand more when we go to the next column. Then we talked about 4 different methods, right? That we liquefied. Now we are generating somewhere in Middle East, Northern Africa at very low price of renewable power. Right? And so you could already see the hydrogen production price by electrolysis is much lower compared to this location. So I generated 4.3 H2 carrier. So from this step to this step is the liquefaction process. So I liquefy, I generate at 4.31, but then I have to put a lot of energy to liquefy it. It's already at 8.21. Then shipping costs somewhere around €0.25 per kg of hydrogen. Boil off somewhere around 0.1. So I landed at another location at 8.55. then we have to gasify it. It's somewhere around 9.4. So you could already see, if you are at this location with a renewable power price is 174, it's still better to produce hydrogen there instead of producing somewhere else and take all this pain. But end of the day, I have to pay high price for my hydrogen. Right? So that's the first one, just a quantitative comparison. The synthetic natural gas route, you could see the efficiency loss from gasification, or let's say where you generate hydrogen and go to the carrier state, it's not so much. So what we do, we generate at the same price because generation is same, which depends on this price. This is 4.31 still, but hydrogen which goes into my carrier as synthetic natural gas, its price is slightly lower because the efficiency is a little bit more. We talked on this a few minutes ago that since you have synthetic natural gas, you are transferring less hydrogen actually. It's more carbon. What's inside your ship. So you could see your shipping cost will be higher. Right? So you save something here, this difference, but then you pay more here. Right? Point of is goes lower. So landed price is similar, but then you have to crack this back or convert this to hydrogen, which is 10.75. So it's still higher. Then we talked about these organic components, which we can hydrogenate and dehydrogenate. Another location, you could already see same price, conversion, hydrogenation is at milder conditions, efficiency is more. So the hydrogen which goes in form of these organic compounds into your carrier is much lower compared to other things. Right? But then once again, higher the molecular weight of component which you are transporting, less is the hydrogen you are transporting. Right? So in terms of per kg of shipping cost for hydrogen, it's even higher because these organic compounds are toluene, ethyl cyclohexane or stuff, and the molecular weight is much higher. Right? So, or let's say C2H ratio is very high, so it's simply transporting carbon and other components, transporting it back. Yeah, once again, the hydrogen shipping cost is much higher for this route. The vapor pressure is much lower, so there is no boil off as such. It's no losses in boil off. Lands at 8.5, but you still have to dehydrogenate it. That also costs something. So you ended up at 9.76. But then look at ammonia. To generate once again at 4.31 like other four methods. From ammonia to from hydrogen to ammonia, efficiency loss is not so high. It's a very well established one technology. 5.4 very low. What goes to the carrier? There are some boil off losses somewhere between organic components and synthetic natural gas. Sorry, shipping costs, but no boil off. It landed at 6.85, and cracking ammonia is also very similar to SMR cost, what we saw in the morning. So also we can say very well established technology. And there we have a lower price than generating hydrogen. So what we see from these tables, and we should not draw any conclusion, this is just for comparison purposes. But at the moment, generating hydrogen at location where renewable power is high, there are some methods where you can transport energy. There are components or compounds which can act as energy carrier. That's why this term comes up, energy carrier. But that's how the economics looks like in the moment. And ammonia, since ammonia shows huge potential, that's why there are a lot of ammonia transportation and ammonia synthesis using ammonia and renewable hydrogen projects are coming up. Similarly, on the other side of the world, you have to crack this ammonia, so ammonia cracking plants are also coming up. But as we said, disadvantage of this route is ammonia safety issues. Right? And when we talk about tankers, we're talking about 60,000 tons of ammonia transportation. Right? So on sea, it's not a big issue, it's only a few people on the ship. But when this ammonia is transported to shore, then you have huge ammonia tank farms, and there it's a serious issue. So that's a major disadvantage. But yes, at the moment, research work is continuing on these steps, but this is already kind of industrialized, so a lot of ammonia transportation, ammonia capture plants coming up. Yeah, so we saw at the moment only 4 carriers, but there are others out there. To keep it simple, I included only 4 for now, which have already passed the conceptual stage, right? But people are still looking for new carriers, and the main criteria we saw already should be low in toxicity, low in flammability. It should have high energy density, low molecular weight. Should be in a transportable condition where you do not have boil-off losses. So to keep the shipping cost, boil-off cost low. People are also focusing on increasing efficiency of different steps, where you do hydrogenation, dehydrogenation. So a lot of efforts at the moment on organic carrier, hydrogenation, dehydrogenation steps, efficiency increase. So for example, we talked about the integration, right? So you transport liquid hydrogen, it comes at shore, and you have to gasify it, and there is nobody who can make use of this cold liquid at very low temperature. You just have to gasify it using air or cooling water, river water, sea water, whatever. It means energy is lost in atmosphere, right? So integration scheme people are heavily looking at to have synergies between 2 processes, 3 processes. So kind of hub model, they start to build all these regasification plants at one location or a location where other industries are there or consumers for refrigerations are there. Right? So kind of what we call here is economic zone, where you have a lot of industries coming in, and then they find synergies between them to have overall optimization. You could already see you're generating renewable hydrogen somewhere in North Africa, Middle East, transporting it. It's a collaborative effort, not between 2 companies, 2 societies, but 2 countries or different countries rather, because these operators, ship operators come from a different country. You are generating somewhere else, you are transporting it to somewhere else. Yeah, it's a major collaborative effort. We already saw there is no one solution which fits all. So at some locations where you can find some integration schemes, probably liquid hydrogen transportation is cheaper. So there is no one solution for which can be applied to all locations, all countries, all. Each, as we already saw, each has advantages, disadvantages, and solution is very specific to country, location. Yeah. We already talked about such ideas need supportive government policies.